Thanks, Matt, for the introduction. Yeah, the title of the talk is The Next 700 Verified seL4 Platforms. And before I explain what that means, we're also part of the INSPECTA project in the DARPA Provers program. And our objective there is to make ourselves as obsolete as possible, so to reduce the reliance on formal verification experts for when you want to use verified platforms and verified properties of seL4. Okay, 700 platforms. Why this oddly specific number? It's a reference to a paper by Larry Paulson, The Next 700 Theorem Provers, that introduced the Isabelle theorem prover. And that itself was a reference to a paper by Peter Lankin, The Next 700 Programming Languages. And what all of these have in common is that they take an instance of something and make it generic to apply to many things. And that is what we're going to do with the seL4 proofs. So it's about platforms and configurations. These are the seL4 platforms, or these are the platforms that seL4 currently runs on. So you can, if you get one of these boards, you can run seL4 on them. And at the beginning of last year, before our project started, these are the platforms that the verification applied to. So you could run seL4 on other platforms, but the verification of seL4 would not apply to that. You would have to, contract Proofcraft, for instance, to make the verification apply on one of the other ones. And as of Monday, these are the platforms that the verification applies to now. Yeah, so that's all of the ARM platforms, 100%. RISC-V, I'll look at next, basically. So you can pretty much pick any board that seL4 supports, and the proofs will support that platform too. There's also even a new platform, IMX93, that was ported. That seL4 was ported to end of last year. And the nice thing about that is that I didn't have to change anything at all in the proof to make that work. And that's where we want to be at. Of course, if you take a new board that's sufficiently different, the verification might still not apply, so you still need to try it out and run the proof. But chances are pretty good that if it's just a variation of the theme, that it will work. All right, in the future, I don't want to just support more platforms. I also want to support the settings and options as well. So when you configure seL4, like open up CMake and go into the configuration, there's a whole bunch of things that you can set and unset and tweak parameters and so on. And the verification applies currently to a very restricted set of these. And the reason I'm thinking, well, that we can do something about that is adding a platform is basically a lot like tweaking some of these options and setting some values. So the techniques that we're using to support more platforms will apply to supporting more options. It will be more work that I need to do to actually make the proofs generic in those options, but it should be possible. All right, so it's not really 700, it's more like 1 trillion. But and it's, don't quote me on the exact number. Bonus points if you can figure out why that is a round number. Okay, so what is behind all of this? It is verification with conditional compilation. Before I get into that, maybe to orient ourselves where we are, this is the picture of the seL4 verification proof stack. Lots of layers, lots of proofs. If you want to make the proofs generic in something, in like say a configuration parameter, you have to probably do work in all of these, but there are existing techniques for making proofs generic in something or abstracting proofs over something. That's not, it can be hard, but it's not new as such. You don't need new techniques, you just need to apply them. What I want to talk about today is where the wall breaks. It breaks when you hit C. C doesn't actually have these nice mechanisms to make things generic. And the proof between C and the next layer up, that's where stuff breaks and where it gets complicated. Okay, so why is that? Conditional compilation, I already gave that away. It's conditional compilation because all these options that you set in CMake or when you change platform configuration parameters, they become C preprocessor hash defines. So, values that are either defined or not, values that have a certain value, like, I don't know, here the physical address of user device top, for instance, Or some might even be symbolic register names and things like that. So that's where they end up in C. And so why is that a problem? Well, it's a problem because C verification is after preprocessing. So what we see is not one kernel, but many, many different code bases. You know, if you take all of the space, about 1 trillion of them. And of course, making the proof generic means you want to write one proof that applies to all of these. And to see why that might be a problem, random bit of code. It's not actually one that I made generic, but it nicely demonstrates why that might be hard. Depending on how you set these options, that might come out with different code. So this is not the real C code that the compiler actually compiles or that the verification tool sees. This is the real C code, maybe. Or maybe that. Or maybe that. And if you had a quick and keen eye, you will have seen that this code appeared nowhere on the previous slides. And that's because if you change a config option, you might be actually reading a completely different C file. And you know, that's AR64 and stuff, AR32 for instance. And you know, you might still want the proof to work for all of these. So, all right, what can we possibly do? The question is hard enough to maybe take a step back and ask, well, okay, why are we doing verification after preprocessing? Wouldn't it be maybe better to do it before, if that's that's so hard? Okay, well, why? The preprocessor is a text replacement engine, and to be more precise, it's a token replacement engine. But generally, it just it's used for simple things, like I showed on the slides before. So a value is either defined or just not defined, or it's some constant that I don't want to type out as a magic number, or maybe in some cases some really simple function. Those are the easy uses, and we can probably deal with those. But here's something a little bit more advanced, and this is not made up. This is out of seL4. So let's assume I want a macro that evaluates to 1 when the argument is defined, and it evaluates to 0 when it's not defined. That would be very useful, for instance, if I want to turn an if-def into an if. That's exactly what I would need, right? How would I do that? Well, here. C programmers will probably go, yeah, klar, but that's not a problem. Here's some of the slightly more exotic operators. So one is the double hash is concatenation, so taking 2 tokens and making it into 1 token. And the ... here means just more arguments would be allowed. And I must resist talking you through all the details. Instead, I'll show you an example. And so if you take one where the config option is set, then it will evaluate to 1, and it will be fused with this macro test thing here. So it'll be macro test 1, which I happen to have defined as a comma. All right. So I call the next macro with comma. And that makes this thing here have 3 arguments, of which the second one will be returned. So 1. Cool. I mean, it's a complicated way to get 1, but it does the job. The reason why we're doing it in this complicated way is, well, we also want to return 0 when it's not defined. And that's a little bit harder, because if a macro is not defined, it doesn't get replaced with anything. It just stays there as the string that you typed, right? So this becomes macro test other, which nobody has done anything with, so it doesn't get replaced. And so specifically, it's not a comma. And so therefore, in that last macro here, we only have 2 arguments. The first one is complete garbage that the compiler would absolutely choke on if it ever got to see it, but it doesn't get to see it because it's thrown away. I've just returned the second argument, whatever I do, and that is 0. All right. So I can see that the C programmers in the audience are nodding. This is hard, but it's cool stuff. And the form methods people in the audience go slightly green in the face. All right. So this is not talking about syntax trees or anything nice, right? This is really just pure text replacement, and it doesn't even have to be syntactically well-formed or anything like that. If you stare at this bit, also from seL4, let me draw your attention to that. Or is a binary operator. It takes 2 arguments. You cannot have a closing bracket just after it. That is not syntactically correct for anything. But of course, this is before pre-processing. And if the macro is defined right, and in this case, it will either keep everything or throw everything away. And both of these options will yield syntactically correct programs. So everything is fine once the compiler gets to see it, or in our case, where the prover gets to see it. But before that, the input is not a thing that you can even properly parse in any variant of C that makes any sense. So that's why we're doing it, the verification after pre-processing. And if you look at the standard and the language, the meaning of C literally is first you pre-process, then you parse, then you compile. You can't swap the first two, it just doesn't work. All right, can we avoid that? Well, not really in C. C is designed to work with a macro language. It really loses power if you don't have it. So you're stuck with it. Maybe when you do new languages, don't do the macros that way. But we can avoid it somehow. Like, we cannot solve the fundamental problem, but we can look at how are macros used in seL4, and can we cover those cases? Or maybe, if there are cases that we can't cover, can we maybe avoid those cases? And it turns out that we can. So the main things that we need to cover are numbers, constants. That should not be so hard, right? And options. So mainly if-def. Either a bit of code is there or it's not there. That's really it. If we can cover those two, we can cover 90%, I would say. Okay, numbers. Well, how do you make a proof generic in a constant? That's not hard. So you define the constant, you give it a name, step one. Then you never talk about the value of the constant, you just assume some properties about it. Like, I don't know, it's greater than 0, it's smaller than that, it's aligned to something or divisible by something else. You never unfold it, you do your proof with just those properties, and if you manage to do the proof, you then at the end only need to check that your value satisfies the properties, and then you're done. And if the value changes and it still satisfies the properties, the proof still holds. That's how you make it generic. So the same proof will apply to all the values that work. Well, if I want to apply that, here's my nice program in C before pre-processing. I run the preprocessor, and I can't even do step one. There is no name max RIQ anymore when the prover sees it. And you could say, okay, well, 187, I happen to know this is max RIQ. So whenever I see 187, I will call it max RIQ. Okay, maybe it works for 187, but it does not work for -1 or 1 or 2, or those could be other things. So let's not do that. I actually do that once, but it's fine. These are the three options that kind of sort of work. So the first one looks nicest, but C happens. So the first one is you just say const, and it's a global constant. But in C, it's not a constant. You can say const as much as you like. Somebody could take the address of that thing and change it in the pointer, and the compiler will say, yeah, sure, go ahead, change my value. I'm not a constant. And so therefore, the compiler knows this, of course. And if it can figure out that nobody takes the address, it will actually be fine, and it might use it for optimization. But generally, it will not use it for constant folding and optimization and so on. And we really want that to happen. You don't want big formulas that are evaluated at runtime all the time. So that one, I think, is only used once or twice in the kernel, where we have verified that it is okay. I think for IRQ invalidness is one of those, for instance. The one that we do most is actually enums. It's a bit of an abuse of mechanism, but an enum, you can have a value name, a name on the left-hand side and a value on the right-hand side. Perfectly legal C. The name is symbolic. In my proof, I will always just refer to max IRQ, never talk about the value apart from its properties, and things are fine. The only problem is it only works for int. Like if you need unsigned long, that's already outside of the standard, and the verification C parser will actually refuse to parse that. So the one that's left actually does work in all cases that I can remember. Well, maybe one. But so what you do is you wrap it in a static inline function that is really just return the value. The compiler is smart enough to just throw all that away and do constant folding and all the optimizations that you want. And in the prover, you just don't throw it away. You can see it's inline, but you're not forced to inline it, right? You can treat it as a normal function call. And that'll work. The only downside is, okay, it's not really idiomatic C. No normal C programmer would go and write these things, but we don't need to be normal C programmers. That's okay. And so we basically mostly use the middle one, and we escape to the last one when we have to. There's one more instance where numbers are mentioned, and that is in types. And the only position in a type in C where you mention a number is the size of an array. But we do have arrays, and we do write things like, I don't know, the IRQ table has max IRQ plus 1 entries or something. I did not actually check if we have that. I just put it on the slide as an example. So what currently would happen is, after pre-processing, it's that. The C parser will go and evaluate that, and in Isabelle, it is actually okay to write a number as a type. If you know a little bit about simple types and theorem proving, you might think that's weird, but that's okay. That one we can do. The one that we cannot do is this one. We cannot write max IRQ plus 1, even just straight in Isabelle, because the plus 1 is a term and not a type, and you can't have a term inside a type. That would be dependent types, and we don't have them in Isabelle. We also don't like them. Way too much trouble. All right, so we can't do that. What do we do then? It turns out that all the array sizes in C programs have to be compile time constants. And so that means, and I don't really need a term inside my type in the theorem prover. I know it will always be constant during the entire proof. It will never need to vary. So what I can do is I can invent a new small command in Isabelle that takes a type name on the left-hand side and a term on the right-hand side. And what it will do is it will evaluate the term to a number, and it must be able to evaluate to a concrete number. So max IRQ, I might not know what it is when I read the program. Well, when I read the program, I do know what it is, but I might not want to know what it is when I write the proof. But it will exist, and so it will, for instance, evaluate to 188. But I will never look at the 188. I'll do a definition in the background that is the same as before. The IRQ size becomes 188. But instead of using that, the command proves a little theorem that says the size of the type on the left, which is how I can have a number as a type, it's just the size of the type, equals the term that I gave it on the right. And that is the property I'm going to use in the proofs. And that's really what the C code wants to generically express, that the size of that array is max IRQ plus 1. And so if I use that property in the proofs and not the number, my proof will still be generic. That's a cute little command, and yeah, that works fine. It has so far covered everything that we needed. Okay, we've done numbers. What about Boolean options? In theory, also, like in the proofs, they're easy. It's just an if then else. And instead of evaluating what the condition actually is, you do a case distinction. If the condition is true, then you do this branch. If it is false, then you do the other branch. And you write one proof that deals with both branches. Okay, fine. It's now generic in whatever the condition turns out to be. All right. In practice, well, why do we do this if-def stuff? We could have written if in C. We do it because we actually want code to disappear from the kernel. So if you have an AH32 kernel, you don't want the RISC-V code in there. Or you have, I don't know, you don't support hypervisor extensions, you don't want all the hype code in there. You just want it to be gone from the binary. So what we need to do is we need to replace the if-def with something that the compiler can optimize away in exactly the same way, so it gets exactly the same binary, but that is an if then else. And that actually kind of works. So going back to my fictitious example, fictitious in the sense that I have not made it generic, and focusing on the bottom part, this is how I could write it as with just if then else. So it's no longer if-def, it's just if. And let me open that pointer. Instead of just having the macro here, which may be defined or not defined, I have config set, which internally calls this isSet thing that we had on the slides before. So that will evaluate to config wrap of 0 or config wrap of 1. And that actually gets me through, right? Now what the theorem prover sees is a normal if then else, which, okay, it might have a constant in the condition part, and the prover could go and say, I don't actually need to consider this other case, but as a user I can tell it to, no, yes, it's 0, but assume maybe the 0 might not be 0 and do the case anyway. And if then next time I run the proof it is 1, then I have done the case and it will run the proof. So the price I pay is, unfortunately, if I put that into C, all these names that I may not use, because, for instance, the option is not set, they need to exist. So it's illegal to have an if branch that calls functions that don't, where the name doesn't exist, or where the type names don't exist. So in non-hypervisor code, I would now have to declare the names that are used in hypervisor code. That's some noise in the namespace, but they can be empty. They will never be called, and they will actually fully be optimized out of the binary. So like this branch, when the compiler sees a 0 up at the front, will just be completely gone from the binary. So it doesn't really matter what those names are, but they will be in the namespace. That is the price we would have to pay. And so if I do that, I can do a proof for both cases. In fact, most of the time, this has happened so far for the platform support, I did not actually need to pollute the namespace much. Maybe there's a variable that is not used, but it's declared anyway already for other reasons, and so on and so forth. If I did something big like hypervisor extensions in one proof, then yes, maybe. But we already have hypervisor extensions as a separate proof architecture. So we have currently 5 big parallel proofs for seL4, and hypervisor extensions for AH32 are one of them. All right, so it'll leave me with the same code as I had before, but I can do a generic proof about them. And that brings me to the end. I'll still do some more talking, but about the last slide. But okay, what have we got? Well, currently all of the ARM platforms are supported. I'm probably going to look at RISC-V next, or maybe at some of the options. Not entirely sure, but from the experience so far, the trillion different kernels look entirely achievable. It's not, such a wild idea. The number is big, but okay. All right. What else is happening on the verification space? Yeah, just briefly, I think last summit, or maybe the summit before, we talked about AR64. That is still happening. The integrity proofs have finished last year, and we're doing confidentiality proofs this year. So maybe at the next summit we might talk about those. Who knows? After that, AH64 will be at the same security proof level as ARM, like AH32 and RISC-V. MCS proofs are still in progress, and stuff's happening. I will not make any promises when they finish, but it's looking pretty good. And multi-kernel proofs are also in progress, so stuff is happening there as well. All right, that is it from me. Thank you.
We have a few minutes for questions. We only have one microphone, so I'm just going to ask you to call out your questions nice and loud. Go on.
Like the new constructs that you kind of refactored things to make the generic verification possible for the platforms, is that going to apply for options for the kernel, or do you envision you also need some more constructs, like hard problems to solve to support different configuration options?
So to try to summarize the question for the recording, will the same mechanisms apply for options as well, and not just for platforms, right? My optimism says sure. There might be one or two more things to take care of. But most of the options are of the same form, where, I don't know, I configure the size of the initial C node. That's just a constant. Or I don't know, I don't want the timer driver register updated when I do VM calls or something. That's just an if-diff. So most of them, I would say 80% of them will be doable with the same techniques. It's mostly a question of actually doing all them. That's quite a bit of work. And yeah, discovering maybe the 20% where things are more interesting. But maybe those can be rewritten. So one of the things that we definitely do in seL4 is if it's too hard to verify, then write different code. That's fine. That is easier to verify. That does the same thing, of course. Okay, to summarize the question, the problem is that C doesn't have the abstractions that we would like for verification, and have we considered using a DSL instead that gets rid of the preprocessor? And yeah. I mean, very briefly, yes, but no, in the sense that we do want standard tool chains to work, basically. So seL4 compiles with normal GCC and normal Clang, and we want to preserve that, basically. That's really it. So, and if you add a DSL on top and verify at that level, then your compiler and semantics for the DSL all become part of your trusted computing base. So we want to be, the seL4 verification wants to go as far to the bottom as it can. So C is not even the last level, right? There's also the binary verification step afterwards, which, not for all architectures, but for AH32, yes. And if we added a DSL, we would need some verification for what the DSL does. I mean, that's not impossible, but it would still need to be done. So.
You mentioned that you were covering like numbers and option booleans and support options. I'm surprised, guarded with C preprocessor macro, like type defs didn't come up. Like some integral type that's 32 bit wide on this architecture, 64 bit wide on that architecture, where the assumptions are just a different flavor in the proof.
Yeah. So the question is basically, what about types? So for instance, on AH32, you have 32-bit types. On AH64, you have 64-bit types. The mode and architecture switches are really big switches. And for those, we actually have different copies of the proof right now already. So that's from before we even started making things generic. And we think we will keep those. So when things really change drastically all over the place, then we will stick with, okay, we have 2 copies of this proof. On the more abstract levels, there is actually in the same INSPECTA project a work stream to make these more generic as well. So there's a generic part that can deal with whatever type size you have. And then some architecture-specific size that talks about, okay, what about these specific page tables? But your generic C-space functions have only one proof, for instance. So that does happen, but not at the C level, probably. That'll still be a copy.
Take one more question.
Okay.
So, looking at this and knowing C++, I see that, for example, const export, modern C++ would probably provide a very good solution for this. Did you consider using C++, maybe the C subset plus const export, and that's it?
So did you consider using C++, which does actually have constants? Again, very briefly, but yes, no. So, I mean, the way you phrased it could actually work. So I should, to be fair, I should repeat the entire question, which is, use a subset of C++, which is basically C and just has const. And const expression. Yeah. But I mean, there's all this existing infrastructure already. Like if we started the project from scratch, maybe, but drawing in an entire C++ toolchain is, compared to C, which really is simpler than C++, even though also terrible. But, it probably too much trust needed to do that. Sorry, I didn't catch it. Ah, yes. So Inden is pointing out const expression is coming to C, Another 10 years and we will have it. Of course, we're standardized on C99, but hey, we might add that one feature, actually, why not? Okay.
That's all we have time for. Let's not go on.